Hello students, in this video we'll begin our discussion of scalar conservation laws. Let's be given a function u of x and t. Here we think of x as space and t as time, typically. X space, t time. Okay? And then what we're going to do is we're going to consider the following partial differential equation. So if, then if h is a smooth function. Doesn't have to be smooth, but let's just assume it's a smooth function to start to get some bearing on the problem. Then consider the PDE. It's going to be a first order PDE. It's going to look like this. It's going to look like ut plus h of u, and I'm going to do the x derivative of that h of u and set that equal to 0. And we can specify some initial condition as well, okay? So what I can do with this over here, we're just thinking of x as a one-dimensional thing for the time being. We can generalize to higher dimensions as well, but this is our tinkertoy version of a scalar conservation law. Now, these are very important. We'll see particular examples of this soon. Now, what I'm going to do is the following. I'm going to fix two values a and b. So for any a, b, we can integrate with respect to x. Okay, well, that's easy enough. I'll have the integral with respect to x. I'll have d by dt, the integral from a to b of u of xt dt. There I've pulled the t derivative out of the integral, so that's exactly what I get when I integrate this t derivative term over here. Then I have plus, when I integrate with respect to x, the fundamental theorem of calculus tells me this is going to be h of u of bt minus h of u of at. And this will be equal to 0. Okay? And this equation over here is referred to as the scalar conservation law. So this is our scalar conservation law. It's our conservation law. Okay, let's call that star. Okay, so notice, and let's call this pound. Okay, so I have star and I have pound. So equation star is true. It is defined from a wider collection of functions u, right? Star is well defined for a wider class of functions. U. Okay? So we'll say that a solution of the conservation law is a weak solution of the PDE over here. So we say that a solution of star is a weak solution of the PDE pound. Okay? Now, oftentimes in physical problems, you start with the conservation law. You might have a conservation of mass, a conservation of momentum. You have some conservation law. You can differentiate that conservation law formally and attain a PDE. That's typically how PDEs come about. They come about from physics for the most part. So almost everything I study in my research comes from physics, essentially, right? And so there's a physical problem. There's a conservation law. You differentiate the conservation law, you get a PDE. We analyze the PDE. We analyze the PDE in terms of the strong solutions, the solutions of pound, and the weak solutions, the solutions of star. If we're really lucky, in more general theory, it can be the case that weak solutions actually become strong solutions. That's a beautiful thing that happens for elliptic PDEs. We'll discuss that in further videos. Great. Now, let's suppose, and this is typically the case, let's suppose now that the function u for the conservation law, u has a jump discontinuity. At x equals xc of t. So for a particular time t, we know that the solution u is going to jump at that point, okay? So there's a jump discontinuity. Jump discontinuities cannot happen for pound, right? Because that's these things are differentiable. Differentiable functions don't have jump discontinuities. But for the conservation law, it's conceivable there's a jump discontinuity, okay? And it happens at this fixed point, x of t is equal to c of t. Great. Now, of course, we know this xc of t lies between these points a and b. So if A less than xc of t less than b, then what we can do is the following. Then we can look at this equation over here, and we can plug that into the equation. We can take this, where this x of t is xc of t, and plug it into the equation, and then see what happens over here, okay? So here we go. So now what we can do is we can take the conservation law, then 0 is equal to h of u of b of t minus h of u of a of t. And then I'm going to break this integral into two parts, right? Then I have plus d by dt, the integral from a to xc of t, u of xt, dt, plus the integral xc of t to b, u of xt, dx, right? Now what I'm going to do is I'm going to do the derivative. Now when I differentiate this integral, I'm going to have two terms from each of these expressions over here, right? So let's focus on those two terms over here, right? So what are we going to get? We're going to have 0 is equal to h of u of b of t minus h of u of a of t. Beautiful. And then I'm going to have plus xc prime of t. And then I'm going to write this as the value of u going from the right, going from the left, right? So I'm going from the, if I'm below this, if the x is in this range over here, the x value in this, that's a dx, of course, right? The x value in this range is less than xc of t, so I'm going to write u sub left for the left limit as you approach that point xc of t. So u left over here, the left limit, okay? And then over here, then we have plus the integral from a to xc of t, u of x of t, with a t derivative over here, dx. Then similarly, we have minus xc prime of t, and now we're going to the right, right? From the limit from u from the right of that function of that jump discontinuity, and then plus the integral from xc of t to b, u of x of t, dx, with a t derivative inside there. Excellent, okay? Now what we're going to do is we're going to let b decrease to xc, so we're going to let b, if b decreases to xc of t, and if a increases to xc of t, remember this is true for any a and b, then what's going to happen to these integrals over here? Then these integrals over here, if b decreases to xc of t and a increases to xc of t, those integrals are going to vanish, and you're going to have the following limit over here. You're going to have 0 is equal to what? Is equal to h of what? H of, as b decreases to c, that's a right limit of u, so that's going to be the right limit of u, minus the left limit of u, h of the left limit of u, and then what? And then plus xc prime of t times the quantity what? Times the quantity ul minus ur. And what does this imply? This implies something very beautiful. This implies that xc prime of t is what? Is h ur minus h ul over ur minus ul. In other words, the speed of this shock, so this is a shock curve, so this curve is a shock curve, right? And this condition is called the Rankine-Hugoniot condition, Rankine-Hugoniot condition, okay? In other words, if there's going to be a gradient discontinuity, a gradient catastrophe for these systems, these equations over here form pound, then I can exactly track the speed of the shock by this equation over here. So this is a beautiful formula. It says the relative jump that the solution takes controls the speed of the shock. So the larger the jump is, the faster the shock will propagate. The smaller the differential is, the smaller the jump discontinuity is, the slower the shock will propagate. So this equation over here, this formula for psi, this Rankine-Hugoniot condition, is going to help me find the dynamics of it will help me determine shock dynamics, and then we can consider more complex systems where we have multiple shocks, or we have situations where there aren't shocks, where we have rarefaction waves. We can have all sorts of different situations for these scalar conservation laws, which we'll continue to discuss in further videos. Thank you very much.